Hello, my name is Johanna Schröder. I'm a PhD student in the group of Matthias Ahrens at the University of Bern in Switzerland. Today I want to talk about the gas diffusion electrode setup for testing catalysts of water electrolyzers. Catalysts are normally tested using rotating disc electrodes or directly in a membrane electrode assembly. The use of both setups includes some challenging aspects. Assembling of PEM electrolyzers, for example, is time-consuming and special equipment is necessary. For RDE setups, on the other hand, the use of high temperatures is challenging. Bernd et al. Were additionally presenting a stability test comparing RDE and MEA, showing some contradictions in performance. In the fuel cell community, recently gas diffusion electrode setups were presented, as there no mass transport limitations are observed as compared to the rotating disc electrode setup. In the gas diffusion electrode setup I'm using, humidified gas is introduced into the cell, passing the carbon gas diffusion layer and interacting with the catalyst. The catalyst layer is separated from the electrolyte by a proton-conductive nephine membrane. So far, I was using the gas diffusion electrode setup for performing accelerated stress tests. Additionally, we can couple the gas diffusion electrode setup with different analysis techniques, as for example small-angle X-ray scattering. After using the gas diffusion electrode setup for testing of fuel cell catalysts, I was wondering if it's also possible to use the gas diffusion electrode setup for testing catalysts for the oxygen evolution reaction. I was using an iridium oxide catalyst from Alpha ESA that we chose as benchmark catalyst, as it's accessible for everyone and used in many studies. The first parameter I was looking at is the gas flow rate, as we are inducing the water that is needed for the oxygen evolution reaction by humidified gas. Investigating different flow rates, it can be seen that between 40 and 190 milliliter per minute comparable activities are reached. And also the Tafel slopes are linear. So, in the range between 40 and 190 milliliter per minute, it seems that enough water is transported to the catalyst layer. As testing of electrolyzer catalysts is normally done in RDE setups, I want to show a comparison of measurements that were obtained in the RDE as compared to the gas diffusion electrode setup. Comparing the results at 30 degrees, it can be clearly seen that the activity reached in the gas diffusion electrode setup is comparable to the RDE measurements. However, at 60 degrees, the activity is differing. In addition, the current density in the RDE measurement is showing quite a large deviation. This deviation at 60 degrees can be explained by the instability of the iridium oxide catalyst in the RDE setup, as during cycling a clear activity loss is observed. As substrate for the catalyst, I was using a carbon-based gas diffusion layer to show that the carbon was not degrading during our performance measurement. I was doing a stability test. Looking at the results of 3 repeats, we can see that no strong degradation is observed that could interfere with our performance measurements. As last topic, today I want to talk about the influence of the substrate, comparing the carbon-based gas diffusion layer with the titanium felt that is typically used in electrolyzers. Comparing the results obtained by the use of both substrates, we can see that comparable activities are reached. So, as a conclusion, we can say that in a gas diffusion electrode setup I was using, it's even possible to use the titanium felt. I hope I could convince you that the gas diffusion electrode setup is a straightforward testing device for electrolyzer catalysts. If you're interested in more details, please check my recent publication in Jack's Code. Finally, I want to thank my colleagues, collaborators, the funding, and you for your attention.